I'd like to thank everybody for coming today, and it is with great pleasure that I introduce Dan Cerutti to all of you. Dan studied as an undergraduate with Charlie Catania at the University of Maryland in Baltimore, and then he went on to do his PhD work with Phil Heinlein at Temple University, and he's now a research associate professor at Duke University, Department of Psychological and Brain Sciences. He teaches classes in learning and research design, and he collaborates, of course, with John Stead on a number of research projects. And he also collaborates with people in the medical school and in the Department of Molecular Biology and Genetics. And Dan has had a wide range of interests over the years. Much of his work, especially in the recent past, has been focused on the concept of conditioned reinforcement. And I could go on and on about Dan. He's really quite talented with respect to equipment and so on. I remember him telling me stories about building all these kitchen chambers and so on. It really is a great pleasure to introduce Dan Cerutti.
Thanks a lot. And also thanks to Bill Warren for inviting me. And I'm going to be talking about choice. In fact, I'm going to be talking about the same things that Grace was talking about, but I'm going to say that, in fact, value is not what choice is about, whether we're talking about simple choice or current chains. Provide a new look. And you can say that they provide a new look, of course. It's not always the case. But in this case, it's a little bit of a glance because we've just really started to explore how time enter into this thing that we call choice. I'm going to begin with a couple quotes. And the first one is terribly convenient. It's by the father of modern experimental methods. It's Francis Bacon, 1625. Conveniently, he wrote an essay anticipating this talk. The title of the essay is Of Delays. And he says, "There is surely no greater wisdom than well to time the beginnings and nonsense of things." And my second quote is appropriately accused of record. This man, Skinner, is also a champion of inductive generalization, as was Bacon. And here we have Skinner with often equivalent where there's a rat and love box and people recorder. And have Kimball records from his book Behavior of Organisms, in which he is, of course, looking at behavior in time. And Skinner was very much a champion of molecular analyses and looking at things in detail in this manner. Here's a very quick overview of what I'm going to be telling you about. The first thing that I'm going to review, most of you know about time and spin schedules, but I'm going to review that because it's very important to make some of the points that I make later on about behavior and choice. So I'll simply provide a short review of timing in simple cases. Then I'll tell you about research we've done on timing and concurrent schedules. And then finally, I'll tell you about some modeling that we've done. Everything is in a very preliminary state right now because the ideas that we're looking at are fairly new and untested. I would like to say that the work that I'm going to tell you about has been done in collaboration with John Stead and Jeremy Days, who's here, I believe. And so let's begin with timing and simple schedules. It's hard to characterize what a schedule is, but here we have a visual response key with one stimulus present and the animal is being exposed to a contingency of some sort. The best contingency to illustrate timing is the fixed interval schedule. And that's very simply the passage of a fixed amount of time and response. And that produces some kind of response of food, for example. So T seconds plus after T seconds elapse produces food. Here are some data from Person and Skinner. These are the pigeon data. But data from other animals is very, very similar. Here we have people records of a large Fi, and now we've got the value of around 12 minutes. The FI pattern is defined by reinforcement. So we begin with a reinforcer, and what we have after the reinforcer is some kind of a pause and response, or a wait. Linear change in ways of talking about waits and pauses. Then we have a period of response acceleration, and then finally we have trial terminating with the related fluid. If we look at parametric data representing the effects of FI value, here we have FI. Here's the study from Cerutti and Pavlovian. These are pigeons, again, rats, and other organisms show the same pattern. Here's FI, or I should say weight plotted against FI. We have a fairly linear relationship. This is what we call timing, for lack of a better term, temporal differentiation of behavior. And it's a very common pattern that we find in all animals. Important things to say about this pattern of the FI scallop is that food is the time marker, in the sense that food tells the organism when to be in time. It tells it something about the delay to the next reinforcer. We know that from various kinds of experiments manipulating food as the time marker. We also, as I just showed you, know that weight, post-reinforcement pause, in the FI is a linear function of time reinforcement, or close to a linear function. It actually depends upon which data set you're actually looking at. I'll show you that in a moment. Then we have the scallop acceleration of responding. We don't have all or none running rates, but we have a little bit of acceleration, which provides a little bit of complexity. We also know a lot about dynamics. I won't get into dynamics here, but many, Russ Church, John Stapp, amongst others, and Jeff Mahiga have manipulated the fixed interval schedule, changing the interval duration from trial to trial. And in general, but not always, what we find is that animals adjust timing, wait times, and other independent measures very, very rapidly. That is to say, all they need is exposure to one interval, and then they'll adjust their behavior to the next interval. We call that one-path tracking. It's a general principle, but it's not an absolute law. There are some cases in which that's not the case. There's a study by L.A. London recently published that shows that it's not always the case. I want to point out, although I was just talking about the FI schedule, the timing is very, very general. And I'm going to argue that wherever you look for it, you'll find it. And so you can look at other kinds of reinforcement schedules. Here's some data from long random ratio schedules. And so what you see is this monotonic positively accelerating function right here. These are random interval schedules from long. These are wait times right here, plotted against a reinforcement interval. Here are fixed ratio data that show a nice linear relationship. And here's an exception to that linear timing rule from Schneider, but it's close to linear. And so timing is seen in other kinds of schedules of reinforcement. And I would like to point out that timing is seen everywhere, including Pavlovian preparations. So these are recent data from our laboratory. These were just collected a couple weeks ago. Finished collecting. This is a Pavlovian procedure with a fish, a zebrafish. A zebrafish is about an inch long, has a brain about the size of a pinhead. And here what we have is a Pavlovian timing procedure in which we have an auto-shaping procedure. The stimulus comes on, some delay later, or called the US delay right here, food is delivered. Occasionally we have empty trials, like a peak procedure, and we look at where the animal pecks at this lever, just like a pigeon picking a key in an auto-shaping procedure. And what we have is this nice, nearly linear relationship between US delays. There's a 4-second delay, 8-second delay, and a 16-second delay in food. Delay again is that interval time between CS onset and food delivery. And here's response latency. And so what this fish is doing is basically learning the time which food is delivered. It indicates that by hitting the lever just a few times. We have plotted here not only the first response, but also the last response. So this little tiny fish shows time. This is just one of many examples of Pavlovian timing. And this is not new, by the way. Pavlov did this. Pavlov did when he was in lake conditioning his dogs. They showed you timing. We talk about timing. He also found it in terms of conditioning. So, some conclusions here. Timing manifests itself in all stages of reinforcement. I'm making a broad claim here, but in fact I believe that to be true. And we get very, very nice reliable functions depending upon the schedule of reinforcement that we're looking at. We get linear functions with F5s, and we get other kinds of functions with other schedules. But what I really want to tell you about is concurrent schedules. And this is called choice. And you pointed out in 1961, Wittgenstein wasn't talking about choice, he was talking about response strength. I'm not going to talk about response strength, I'm going to talk about response timing. But definitely I have choice of quotes here because I don't think the implications of doing this procedure is actually a choice. In a choice procedure, we have two responses, R1 and R2. Typically, people spend temporal schedules. There's other things that we can do here, but typically we're concerned about accounting for behavior and temporal contingencies. Usually those are random interval schedules, and usually we measure response rate. And this is a big difference. The way that we handle, the way that, for example, Randy was talking about concurrent performances is completely different from the way that we talk about performances on simple schedules. When we talk about performances on simple schedules, we talk about wait times, running rates, and things like that. But we completely ignore those things in the research on current schedules of reinforcement. So, let me say some things about current behavior. Here's some data from Tanya from Princeton up here. I find these data a little more convenient. And so here we have plotted the relative response rate and there's relative reinforcement rate matching. This is one of various things that we need to account for. This has been said many times. So here, this is this matching relationship, relative responsive match relative reinforcement rate. There's this simple matching equation. But we also know that there's a tendency towards indifference, and we need to worry about that too. We also know, I should put up here, that we've got a power relationship here. Willie Baum has pointed out that a line fits these data pretty good, but the power function fits better. So we've got several things that we need to account for. Matching, tendency to this undermatching, the tendency towards indifference, and also this power function. Can timing explain matching? Well, let's see how this might work. Let's think about a concurrent schedule. There's R1 and R2 as being two fixed interval schedules, which they rarely been tested, and we know what the outcomes can be, of course. But let's think about it that way. If timing was involved, we know that the animal, which shows this kind of linear weighting, like what we saw in the design of the problem here. What the animal would do is on R1, it would have learned that delayed reinforcement, and it would begin responding at some proportion of that time, which might be like halfway through that interval. R2 here has a longer time to reinforcement. It's going to begin responding at that interval right there. And so what we're going to have in this particular case is we're going to have responding beginning sooner on that alternative that has a shorter time to reinforcement. We also know that we're going to probably, if we arrange this situation, we're going to get some kind of a competition, response competition effect. We know that at about the time that the animal would begin responding on R2, we're going to have some competition from responses on R1 from that alternative that's going to pay out sooner. Now, this is all in theory in a sense. But now what we need to do is we need to ask ourselves, well, in real experiments, with pigeons or whatever, responding on concurrent schedules, do we in fact see the kind of covariation that we would expect from the theory of timing? So do weight and responses covariate? What I mean by that is, do responses with shorter times to reinforcement show shorter wait times than and more responses than responses that have longer times to reinforcement? And so we arranged such an experiment. This is Cerutti 2004 Jan paper, in which we had simple concurrent random interval 15 seconds on one alternative, random interval 45 on another alternative, and then every so many days we just swap the size of these alternatives. And what you're seeing, this is a time series for one animal, the rest of the animals look the same, trust me. And so what you see right there are response ratios, plotted these are the dark points, and So here's left responses divided by right responses, and what's happening right here is that the left is the RI 45, so the n is preferring the right, so we see responding going towards the shorter alternative. Here are weight ratios. These are right weights over left weights. So try to simplify the plot right here. And what you see is that they're moving also. Weight is getting shorter on that better or that shorter time to reinforcement. We do a reversal, we see responses reversed, weights also track right here. What you also see is that weight is varying less than responses, and this is very, very important to know. And there's a better way to visualize these data than simply plotting those ratios. So now what you're seeing is that time series plot is a scatter plot, and so here we have response ratios left divided by right, and here we have weight ratios right divided by left, and we see this nice covariation that we expect from the timing. Now, again, we see, I want to point out that we see less variance in weight times than we do in response times. So we see, so to summarize the findings for the simple concurrent choice right here, weight and responses, they do covary, and so therefore we ask probably responses made about the timing. We also have evidence for equal running rates, that is to say that once they begin responding, they respond more or less the same as on both sides. I'm not presenting those data here. In fact, you can look at the paper and see what the evidence is. And we also know that weight varies less than responses. So weight by itself cannot account for all of the variance in response rates, and that's important to know right here. It'd be wonderful if it did, because we would solve the problem and all the home. But it doesn't. And well, we'll get back to that. So, next question is, can time help us to understand behavior in concurrent chain tasks? In a concurrent chain task, those of you who are here are very familiar with this procedure, but let me run by it real quickly. We have, again, two schedules. In this case, we have two chains. So we have initial 1 and initial 2. And these don't lead to primary reinforcement. They don't lead directly to food. They lead to stimulus that signals some delay to food. That's a typical procedure. So here we have IL-1 leading to red terminal link. It leads to a relatively immediate food. Here we have initial link number 2, which is the same duration as initial link number 1. You don't have to do that. I mentioned some data in some cases in which that's not the case. In this case, we have two equal initial links. IL-2 leads to a green stimulus that also provides food, but with a longer delay to food. Now, we can also think about this task in a purely time kind of way. We can say, let's forget about those terminals completely. Let's pretend we're not even there. And we can say, what is the animal doing in these initials? Well, it's treating this stimulus right here as a signal for a delayed food, not as a signal for that condition reinforcer, which is supposed to have some kind of value that the animal would form. But let's just think about it as simply delayed food. And once the animal is going to show us, well, we know from a simple schedule literature, it's going to show us some kind of proportional timing right here. And so responses are going to be in some time within the interval. Same thing for that other delayed food. So this is exactly the same idea that we have presented previously. For the case of the concurrent random overlap. But now we have a caveat because we have these terminal links which are cutting off initial link responses. And so this introduces a kind of complexity, which I hate to digress from and say that we'll come back to this. But the important question is, do wait times and responses covary again in a predictive way in the timing model in the chain task? So we started to think about this with independent random 47 initial pitches again. FI 15 second terminal on one side, FI 45 terminal on the other side. And as in the previous experiment, we simply randomly did the procedure just occasionally, without consideration of stability or anything else, swapped the terminal links and then looked to see what happens. So now here we have another time series. which the terminal delays are shown by the gray lines right here. So here are reversals, actually, reversals of terminal contingencies. And what you see is that, in fact, response ratios for initial links right now are shown with the dark lines, and weight ratios are shown likewise. The response ratios are left and right, the weight ratios are right, left, and left. You see, once again, the covariant. It looks now like we have perfect covariation of these, and that would be wonderful again. But do note that these are on a lot of scales right here, and not only that, the scale for the wait times is smaller than for responses. So once again, we have wait times covariant with response rates, but in fact, the wait is varying less than responses. There's a scatter plot showing that. It shows us a little bit more clearly. Here's response 11 multiplied by responses right, plotted against weight responses. Weight right multiplied by weight left. And at this point, I should have pointed this out before, but didn't know that this is on a long scale, so there's a powerful relationship. Like it's not a linear relationship. We would, again, it would be wonderful if we had it, because we know at home pretty much. But it's a power relationship right here. It's a very good one. In fact, it's much stronger in this case than in the simple concurrent case. So, what can we conclude about these procedures? Well, in the case of the concurrent chain schedule, once again, we see covariation between weight, initial weight this time, and initial responses. Again, we found that running rates on those initials were approximately equal. Again, I'm not going to show you those results that I published. And once again, weight varying less than responses. It's not an ideal outcome, but it does show that, in fact, there's good evidence for timing in these particular cases. Now, to sum up, both of these concurrent schedules, the simple and the chain, show that behavior may be, or at least it is more about time than we previously appreciated. To look simply at response rates is to ignore important data, and that is that animals are pausing in these procedures. And I should point out that Rick Scholl, many years ago, pointed out that there might be pausing, that he thought that some of the effects on concurrent chains could be the result of pausing. And for those of you who know Rick's experimental history, you know that he studied fixed intervals and he studied pausing a great deal. In fact, he was the first person I turned to when I wanted to understand time. So it's not an incredibly original and it's been wonderful. Now, so far, the data that I showed you are all correlation. They're all correlation. They're not showing that, in fact, timing produces the kinds of response rate differences that give us an action. So I haven't done that at all. Just shown that these things covariant. But we can generate a little bit more evidence that, in fact, timing is involved in choice by using modeling. And we're at a very preliminary level right here, because we don't have the kind of data that we need to develop really nice models, but we found some things that are pretty interesting. So, here's the model that I'm going to be showing you here. It's a very, very straightforward, it's a very simple model. It is like the timing model that we're using by John Staden to model fixed interval performances, and also the dynamics of fixed interval performances. The MTS, the multiple time scale model, but it is a much, much simplified model. So here's how it works. For those of you that don't know the model, the principle is very, very simple. We begin timing with our timer, which is food. We have a memory with that reinforcer, and it's a decaying memory. So the memory is strong at the time of reinforcement and decays over time. Memory. Here are responses. At some point during this memory decay, the animal reaches a point, a threshold, at which it begins to respond. And it responds until it produces the next reinforcer. The next reinforcer, once again, this is a reinforcement memory, which I've truncated here because of the edge of the screen. And again, we have a weight right here, because what's happened here is that reinforcement memory is above the threshold to respond. How do we determine the threshold to respond in the model? We determine it in a very, very simple and straightforward way. We just say that the response rule is simply for the organism to remember to begin responding when b sub I there equals the memory of b at the time of reinforcement, so b reinforcement plus some constant. It's a very simple response. Now, what about the concurrent case? It turns out that there's many, many ways to implement a simple trace timing model like this in the concurrent schedule. One way to model this is to have the organism have two memories, two independent traces. It remembers when the last reinforcer on the left occurred, it remembers when the last reinforcer on the right occurs, and it begins responding the appropriate response rule on each side based on those two memories. And so to look and see what this looks like, well, I guess maybe you can't see this here, but here we have, not sure how this goes. We have the right memory trace represented by a dark line, and it's pumped up every time a reinforcer is delivered. So here's a reinforcer delivery for the left. I'm sorry, this is for the right. And we see that reinforcer memory for the right is pumped up, and now it decays. Here we have a response, a reinforcer that is for the left increases and so on. And the animal in this particular case is keeping track of both of those reinforcers independently, so to speak. There's another way to implement this model, and that is to say that, in fact, there's just one trace. It's a simplification. There's just one memory trace, but there's two threshold rules. And in this particular case, it doesn't matter whether the reinforcer was for the left or whether it was for the right. Whenever the sample is a reinforcer, it remembers that it was a reinforcer, and it distributes its responses left and right depending upon two reinforcement memories. So here are those two memories. So it begins responding to the right over here. At this point in that memory trace, it begins responding to the left, and that's the response 2 over here at this point. The model that I implemented was exactly, well, it turns out that after you run lots and lots of different kinds of models right here, the model that works best turns out to be one trace with two memories. And there's a paper in the press right now, it's being held at Pavlovian, it's the professional John Staff, in which I report all the different permutations of models that you can do. One that gives you the right pattern behavior turns out to be one trace, two memories. And there's the case. I'm sorry, I should stop here. And so, looks like there's two traces here, and there are, it should be just one. And it doesn't matter whether there's a left reinforcer, both traces are pumped up right here. It should be just one trace. Here's another, right, and then there's left. The memory is pumped up in both cases exactly the same way. So, what are the modeling findings? Well, remember, this is actually a pigeon right here. It's a different pigeon than I showed you previously, but the same pattern. So this is a simple concurrent case right here. And here we have left and right responses in the scatter plot following against right weight divided by left weight. What we have is this power function with weight times varying less than response times. But they co-vary. These are the data from an animal. Here's the model. I'm just going to talk about the dark ones right here because they're the ones that are the ones from this model right here. And here we have this nice power relationship. Power function fits these data. We have responses left, right, weight, right, left. And my model uses a slightly better fit, but anyhow, it's the same pattern exactly. So the model is giving us one result that we need. And of course, we built that into the model, so that's not surprising. The question is, what does the model do about matching? And here's what it produces. This is the model right here. It's one trace with two response rules. It's an exponential trace, by the way. That's what works best. Very simple exponential trace. The parameters are these right here. I want to say that the model is exceedingly robust. I did no fitting. The first time I ran it, gave me the results. And in fact, you can push the parameters everywhere. I wouldn't have chosen parameters to show you like A was 5 and 2 was 100. Had I here are the data. There are several plots on here. And the reason for this is that the first thing that I wanted to test with the model are some old findings about how distributions of inter-reinforcement times affect matching. These are data that have never been properly accounted for before. And one of those findings is that if you pit two random interval schedules against each other, like random interval schedules, you get better matching than if you pit two VI schedules. That is, you get more undermatching with the VI schedules. The model shows you that. The random interval data fit that diagonal better than, in fact, the VI data. The model just did this automatically. No fiddling, same parameters, never change the parameters in the model with any simulations. The other finding out there is that if you run VI against an RI schedule, you'll get a slight bias towards the schedule. And in fact, VI, there's a VI five studies on this, so it's only one in some of these studies. These studies are bomb, they've sent a bunch of people who did these RI VI comparisons. And anyhow, the other important thing is that a power function fits these data best. So here we have an undermatching, we have a power function fitting these data best, and we have a very, very, very simple timing model. As I say, this is not this figures of price. Here, pretending data again, and you can see that that's a pattern of results right there. The model does generate a little bit more undermatching than the vision from red. Again, I've not done any real serious fitting of this, and it probably is important to shape that functions. It's important, so I use it exponential because it behaves so well, and it's such a common function for memory that it's an unreasonable thing to do. But maybe that's not the right function. Now, one of the things that this suggests is that we now have an explanation for undermatching. And undermatching may be the product of the animal not responding to the actual inter-reinforcement intervals as the matching law wants and demands. But in fact, what the animal is responding to are the delays to reinforcement from any reinforcer. So, notice what I'm saying is that there are two distributions that the animal could be using on here. My model is saying that the best distribution is that distribution of reinforcement times, which is generated by the last reinforcer. It doesn't matter if it's left or right. The matching model says that the right distribution should be two independent distributions. If we look at, once having done all of this, we actually went back to our RI data and asked, well, what are those distributions? What do they look like? And can we find a distribution of what we call a travel duration distribution that will give us undermatching? And we find exactly that. And so let me explain to you what you're looking at right here. You're looking at the random interval data right here. You're looking at two distributions. These are inter-reinforcement time distributions for the RI 15 second and the RI 45 seconds. And what these are so these are 5-second bins right there. So this is the number of times that there was 5 seconds between a reinforcer on the 15 second side, between each reinforcer on that side. And this is the number of times that there were, this is the 5 second one here, I misspoke. That's 5 seconds, that's 10 seconds, 15, so. And so what you're looking at is the actual inter-reinforcement times. Here what you're looking at is the actual trial duration times. And so these are the times measured, these are the durations, trial durations measured for the last reinforcer. So what you find right here is that, in fact, these two distributions are closer together than these two. That is to say that even though we have the same schedules right here, the two trial duration distributions predict undermatching. They predict undermatching. And so possibly, we don't have proof of this yet, possibly the animals are in fact not responding to the overall rate of reinforcement. They're responding to the specific delays that they get from the last reinforcement. Next question that we ask is, can we prove this? And we come up with an experimental test that in fact they have time through the last reinforcement, not in the sense of the reinforcement rate. And in fact, we have an experiment that was just published about a month ago in JP. This is a German CQBS. This is the first author, and on that paper. And what we did was we studied the case of concurrent FI schedules. So we arranged two concurrent FI schedules. The inter-reinforcement interval on both sides was 80 seconds. So here's, we're going to call these two sides an FI20 and an FI60, but in fact, the inter-reinforcement interval for the two sides is exactly the same. 80 seconds on the FI60 side and 80 seconds on the FI20 side. What was different was how the reinforcers were arranged in time. So if you had just collected a reinforcer on the FI60 side, the next reinforcer was always available on the FI20 side 20 seconds later. If you had just collected this FI20 reinforcer, the next reinforcer was available on the FI60 side 60 seconds later. So what we have now is we have dissociation between overall rate reinforcement, which is identical on both sides, but on each side you have different trial duration times. The question is, what does the pigeon do? If it's timing from the last reinforcer, if it's timing from trial duration, it should show you, is irrespective of the last reinforcer, it should begin responding on the 20 side and then switch over to the 60 side. Irrespective of the last reinforcer, it should always do the same thing. If it's responding to actual inter-reinforcement times, it's hard to say exactly what it's going to do. What it's going to show you is actually pause after a reinforcement. And then what it's going to do is respond on the appropriate side. That is to say that if it just picked up the 20-second reinforcer, it's going to pause and begin responding on the 60 side. If it just picked up the 60 reinforcer, it's going to pause and then begin responding on the 20 side. And what does the animal do? The animal shows us unequivocally that it cannot remember whether the last FI was what it was. It knows it's always timing from the last reinforcer. So here we have data for one pigeon, for the rest of the pigeons down here. These trials, this is a solid line right here, is an FI20 trial, which ends with the FI20. So you can see that these are response rates by the way, the FI20 side and the FI60 side. And so here's an FI20 second reinforcer, but it's basically FI20 second side, sorry, it's an FI20 second side, it's a 60-second reinforcer. So if it begins responding on the FI20 side, doesn't pick up that reinforcer, the responding declines when on the side. It's like a peak procedure. Here's the case in which you do get the reinforcer on the side, so keep responding. It begins on the FI20 side, it gets the reinforcer, of course, you need more data. What's the responding on the FI60 side look like? Well, it's an increase in response rate. So what the animal is showing you is, again, control of the last reinforcer, irrespective of where it came from. And so the animal is actually timing on that last reinforcer. We can apply this model to the case of the concurrent chain. The same model. And note that if we apply this model to the concurrent chain case, we're going to ignore completely what's happening in terminal limits. We're not interested in value whatsoever. We're going to ignore it. One of the findings that we need to account for is the Fantino delay reduction point, which is that indifference grows as initial increases. So I don't have this on here. This is a paper by John Stead and myself in 2003 and then we do some psychologists about the paper and that reviews some of these predictions. But here's a simple way to understand the Fantino effect or the delay reduction, or the initial limit effect in terms of time. So here's a case in which we have short IOs, here's a case in which we have long IOs. Both of these cases have exactly the same terminal duration, so relatively short term reinforcement, mediums and long term reinforcement. Same case right here for long initials. Well, we know that the short initials would have a much greater preference for the short initial than the long one. Let me explain that. Well, you'll notice that, in fact, if the animal is responding here to time for reinforcement, and so it's beginning responding at some proportion of that time for reinforcement, it's going to begin, you're going to have a much larger ratio of differences right here. And So you can see that here you have a 2-to-1 response ratio, and here it's something much less. It's like 3-to-2 or something like that. Now we want, so in a simple form, that's how the timing model will account for finding alignments. But what happens if we apply our timing model to the actual data? And I want to compare here the very, very early survey by Fantino, 1969, in which he first presents his model, the delay reduction model. His data are these, so the actual digit data are these blue points right here. Delay reduction are the yellow points, I don't forget the usual. The delay reduction ratios are here, and TTR predictions, and that's time to reinforcement or that simple timing model, are these predictions over here. And let me point out, let me remind you that this timing model is making no assumptions whatsoever about condition reinforcement. None whatsoever. And it's predicting the findings. It's actually predicting better. We also, I didn't realize that I was going to talk about the next 10 days, so I could have presented some more findings here, but let me just, well, there are some findings. Wait a minute. Here's a more non-intuitive case. Here's a case where Fantino, that's again the 1969 paper, in which he compares different initial iterations and different terminal iterations. He had the VI90 against the VI30, and the VI pitted against, this is a chain, VI90 pitted against the VI30, Both compare his preference for 30 seconds, it's massive. So this is the preference for the RI 30-second terminal link, which delay reduction predicts nicely. He underpredicts it leading to this. So TTR, the timing model, underpredicts it as well. But it gives it qualitatively the same result. We also fitted our model using the data that I did bring to procedures, a vast number of experiments that were done with different initial iterations. These were done in Fantino, Davidson, and others as well. And our simple time to reinforcement model, our simple timing model fits those results equally or better than delay reduction. But again, point out, we're just looking at timing for the initial link, timing for the last reinforcer, nothing about condition reinforcement. So, conclusions about modeling, one-trace models with effects. Predictions include power matching and effects of negative reinforcement intervals. We modeled, I think, for the first time, the effects of having VI schedules, VI schedules, RI schedules, against RI schedules, and of course the fixed interval VI comparison. It makes the undermatching not for reason to believe, we have reason to believe anyhow that what animals are doing is they're timing from the last reinforcement, at least that's an explanation that works. And it accounts for concurrent chain initial reinforcement technique effects. I didn't mention that in fact we can model self-control experiments, again, with the same model that we did in the video that I have on my computer, you can see. So we can measure, we can model rapid and green self-control study. Again, just assuming that larger reinforcers produce slightly shorter load times. That's all you have to assume in the model. The slope of that function is slightly different, which we don't have a lot of data on this much. We're working on this right now, but in fact, we have reason to believe larger reinforcers do produce slightly shorter load times, slightly shorter latencies to this model. So, conclusions. Temporal control, mainly, outcastic data involving a wide variety of operating procedures, and emphasis on causal factors and reinforcement schedules, and unified use of previously defined abstract terms on time and machines. And I would like to end with another group that was right here. Who says we're to admit no more causes of natural things, such as both true and sufficient use for many things. And I think that's what we're making time. As I said, this is a new look at matching, this is a new look at a lot of these findings. It's very preliminary, there are very few people who are working on it, and trying to convince others that it might be fruitful. And so that was very much.
We have time for a few questions, please.
You said a number of times that you didn't make any assumptions about condition reinforcement. Could you elaborate on that a little bit? Do you mean to say that we don't need the idea of condition reinforcement to produce this model, or do you mean that it hasn't yet been incorporated into your model?
No, we don't need the idea of condition reinforcement.
So it's
What I'm arguing that you can account for findings very, very satisfactorily without ever mentioning about value that the animal is actually looking at the condition reinforcer, or which we have calculated a certain value, and saying that we respond to the condition reinforcement control by the delay, but the ultimate delay of reinforcement, irrespective of that.
Okay.
Yeah, it's really a kind of a radical departure from our traditional way of thinking, I must say.
I want to elaborate on that question a little bit. Is if you show that you explain preference if you have condition reinforcers. If you have different delays to reinforcement and condition reinforcers, the onset of condition reinforcers started at the same time. What happens if you reverse that? If you have, how would you expect if you reverse that relation? If you have food being delivered at the same time, but condition reinforcers.
Oh, we expect a difference. Yeah, we expect a difference. Yeah. Actually, we don't know what that's because the problem with a procedure like that is that it's a dynamic thing. In fact, I've been showing a simulation to you. I hope that was obvious. What will happen is, in fact, the length of that initial link will actually truncate the amount of responses that you can have at any time. So there is an interaction to that. But you'll expect something closer to difference.
If there was no truncation, if it wasn't responding was truncated by at the end of the video option 5, introducing the condition reinforcer, you would expect that the animal will just more completely the condition reinforcer.
Would be identical.
You would expect that the animals will completely ignore the condition reinforcers if they didn't eliminate it was and respond to the other.
Other questions?